Today we'll go through the following agenda, including RTP company, who we are, what we do, and why, common problems that you'll encounter with part components for tools, and the solutions we have to offer, including brittleness, strength and rigidity, environmental exposure, warp and shrink, density, cost, support, and innovation. And I'll close out touching on sustainability and a quick summary. So first, a little bit about RTP Company for those that don't know us. We're a global compounder of custom engineered thermoplastics with approximately 1,800 employees and $1 billion in sales. Unlike some of our competitors, we are an independent, privately held global company. This is important, and here's why. As an independent company, we can be completely objective when looking for raw materials, formulations, and solutions to meet your requirement. In doing so, we're able to provide you with the best thermoplastic material for your application at the best cost. Being a privately held company is another important distinction. Rather than making short-term decisions to meet short-term goals, we're able to take longer range view when making decisions. And last but not least, being a global company, we're committed to serving our customers all over the world and well into the future. We work in every thermoplastic resin besides PVC with hundreds of modifiers to develop the right solution for the application. We sell more than 9,000 different types of compounds each year in pellet, sheet, and film formats. And of these, roughly 1,750 are new formulations. Our roots are as a highly technical specialty compounder. And while we still hold on to those roots, we've really become a full-service supplier for anything from something like a highly specialized nanotube PEEK to a high-volume commodity material like talc PP that we can compete with anyone on costs. With over 20 production plants and even more sales offices are located around the world, we are well equipped to serve you with consistent thermoplastic materials wherever your facility or facilities may be located. In fact, we have more than 2 million square feet of production space around the globe with hundreds of extruders and millions of pounds of capacity. Each region can produce the entire thermoplastic compound line in pellet form, and each facility provides prompt local service. This is a slide from our corporate presentation, but it really resonates with me personally, and I'll tell you why. We are a family-owned, customer-centric company, and it still very much feels that way, even though we've exceeded $1 billion in revenue. And by focusing on our customers' needs without a lot of bureaucracy or red tape, we can respond quickly and effectively. So I know that's true because of my time as a product development engineer. If a new application or technology or problem came across my desk and I wanted to go do some R&D or development work, it was just simply a matter of me formulating, scheduling time on the extruder and going down there and running materials, playing with materials, and figuring out problems. And we still operate that day to day. We're a very flat organization. When we have a problem in front of us, we have a lot of freedom to go in there and get it done. Whether that be on the R&D side, the business side, we really want to get a solution to our customers as quick as possible. Simply put, we serve literally every market where thermoplastics are used, from mission-critical parts going into space to very basic low-cost parts. If thermoplastics are being used, we're probably there. That means we've pretty much seen it all and can carry that expertise across all markets we service. I've mentioned compounding compounds a couple of times now, so before we get into it, let's take a quick look at what I'm actually talking about with those terms and what we do as a compounder. So you'll see here a range of raw materials. So let's say we have a base resin, a base polymer. What we're going to do is take that and mix that with additives, put it through an extruder, cool it down, pelletize it, and send it out as a finished product. But if we take that previous slide and break it down, what we're really doing in the compounding process is simply using various additive technologies to improve and deficiencies in neat or virgin polymers to provide a compound that meets all the requirements of a given application. It's a pretty simple concept, but the breadth of technologies involved is not simple at all. As such, RTP company is organized into product families according to their general attributes and the technologies involved. That includes color, conductive, flame retardant, high temperature, long glass fiber, structural, TPEs and TPOs, wear resistant, and finally our sheet division. Today's focus will be primarily structural compounds with a quick mention of some high temp in there. Now that I've introduced RTP company, let's pivot to some of the problems that are commonly encountered in the tool space that can be solved by working with RTP's structural product group. Those issues include brittleness, flexing, low strength, warp and shrink, environmental issues, comfort, and then finally costs and innovation. In keeping with the tools theme, let's dive into the toolbox of additives and technologies that we use in the structural group to address those common material problems. We have modifiers, which we currently break or further break into impact modifiers and polymer blends. And we have fillers, which I break down into mineral or low aspect ratio fillers and fiber reinforcements or high aspect ratio fillers. I'll go into those terms and technologies in more detail as I go through this presentation. First, I need to quickly explain the concept of aspect ratio. Aspect ratio is simply the large geometry divided by the smaller geometry of a filler. The general rule of thumb is as the aspect ratio goes up, the reinforcement property of that filler is going to go up as well. This term will come up a few times, so just keep that concept in the back of your head. Now let's start looking at the common issues you see with tool components. First up is brittleness, or general lack of impact resistance. This is the failure to survive a high force over a very short duration. Impact resistance is an inherent property of polymers, which is also dependent on many things like temperature and part design. But fortunately, there are things we can do to improve upon that characteristic. And that is the addition of impact modifiers. Impact modifiers are just what they sound like. Modifiers used to adjust the impact resistance of polymers. Excuse me. Impact modifiers are going to be specific to the host polymer that they're going into to increase the ductility across those polymers. Very commonly done in nylon. That's probably the most common, but can be done in pretty much any semi-crystalline resin, including PBT, PPA, PPS, and even some amorphous resins. You'll improve that impact performance at all temperatures when you incorporate impact modifiers for the most part, but sometimes they're specifically used for low temperature impact improvement, because as polymers get colder, generally they get more brittle, and that can be a big problem. You do get the side benefit often of a reduced specific gravity. So if we look at a common material that's impact modified, like I mentioned, is a nylon 6,6. That's probably the most ubiquitous out there. If we look at what that looks like in impact modified version under our RTP 200H, your notched IZOD impact goes from only around 53 joules per meter to 961. So a dramatic, almost 20-fold increase in your impact resistance. There is a downside where when you use impact modifiers, your strengths and stiffness will go the other way and generally reduce. As the saying goes, there's no free lunch in plastics, but a lot of times that can be counteracted with other things like fillers, which I'll get into. And I did mention you do get that extra benefit of reduced specific gravity, so that means more material for your money. Moving on to what might be the most common fault that we address in the structural group, and those are low strength and stiffness. Basically, material is not strong enough to survive the load that is applied and or flexes too much as a result of that load. The workhorse technology used to address low strength and stiffness, which anyone familiar with thermoplastics is well aware of, is glass fiber reinforcement. Glass fiber is used in various forms in thermoplastics, but the form we use the most is short glass fiber, otherwise known as chopped glass fiber. Glass fiber improves on a range of properties, including strength and stiffness, creep and fatigue resistance, and even impact resistance in the case of less ductile polymers. Glass fiber can also substantially increase the usable temperatures of polymers, especially in semicrystalline polymers, by improving those mechanical properties at elevated temps. A lot of times it's measured in something you see as HDT or heat deflection temperature. So if we take a look at this graph, as we add glass fiber to, for example, polypropylene here from 10, 20, 30, 40%, you'll get a rather linear increase in your tensile strength. And that's going to be true for most polymers. There usually is diminishing returns around 50% for tensile strength. Your modulus will continue to improve as you add more glass fiber, with the limits usually being somewhere around 50 to 60% maximum loading. The downside of adding glass fiber is your specific gravity or density does go up. While glass fiber compounds are widely available, something that is more unique to RTP company is our extra performance, or XP, glass fiber polypropylene product line. With that, we've combined the latest glass fiber additives and compounding technologies to provide industry-leading short glass fiber polypropylene compounds. XP compounds exceed the performance of traditional short glass fiber polypropylene and even approach the performance of long glass fiber polypropylene in strength and stiffness, as you can see in the graphs, with the standard in blue, the XP in red, and the long glass fiber in green. And this is tensile strength, and this is modulus or stiffness. XP really bridges the gap and approaches that performance of long glass fiber, but then it does it in a short pellet, which aids with the ease of handling, a bit lower cost, and really kind of just bridges that gap. Now, if impact resistance is your primary goal, the long glass fiber is still going to be your best bet. But if you're just looking at a boost in your strength and stiffness versus standard short glass fiber polypropylene, XP is really a great product for that. So those are some common basic issues and solutions encountered involving mechanical properties, but there's plenty of other material properties that can result in part failures based on where the tool lives. Those environmental factors include chemical resistance issues, UV exposure, and elevated temperatures, with each causing degradation in different ways, thus requiring different solutions. Chemical resistance is a property inherent to each polymer and chemical involved, so the best solution to chemical resistance issues is to just specify the correct base polymer up front based on what kind of chemicals the part might see. That's not always straightforward depending on all the requirements or what you may know or not know going into the application. But one of the options we have to address chemical resistance is in the form of polymer blends or alloys. And in alloys, really what we're doing is we're trying to combine attributes that we like in two different polymers and mix them together. So let's take PC PBT, for example. The PC is going to bring toughness and dimensional stability, while the PBT brings chemical resistance and improved flow. So let's say we like the properties of polycarbonate. It's very tough, dimensionally stable, but we are concerned about some chemical resistance issues. We can bring in some amount of PBT into that alloy and boost those properties and also help flow. On the other hand, if we like PBT, it's got good chemical resistance, good flow, but we're maybe having some warping issues, we can introduce some amount of polycarbonate to improve the dimensional stability there. So in alloys, what we're trying to do is take things we like about two different polymers and bring those out into one compound. Next up is UV exposure, causing polymer degradation, which manifests in reduced mechanical properties and color shift. We have two ways of addressing that, UV absorbers and HALs. UV absorbers protect polymer by absorbing the UV before it starts the degradation, and HALs protects the polymer by stopping the degradation once they've started. Good way I've been told to sort of think about this is the UV absorber is the sunscreen and the HALs is the aloe. That's really what we're doing to try to protect polymers. See in this graph, 30% glass fiber polypropylene. When stabilized with HALs, we'll start to drop off a little once we get out into some extended accelerated weathering, while HALs and absorber will maintain those properties even further. I don't have a non-stabilized, but you'd see sort of a steady drop once you get out here in those properties. Last common environmental cause of part failure is elevated temps. Elevated temps need to be separated by duration, as there's two very different things at work. Short term takes into account the changes in material based on the shift in mechanical properties of polymers at elevated temps. So basically, as thermoplastics get warmer, the polymer chains will move more freely, and that generally pushes your strength and stiffness down. So if we take a look at what that looks like, and for example, a stress strain curve, and this 30% glass fiber polypropylene at negative 40, we have on the y-axis the tensile strength, basically. It's very stiff, pretty strong at negative 40. We move to room temperature. Our stiffness, or the slope of this line, goes down. It fails at a lower stress, and so on and so forth as we move into higher temperatures. Those properties are generally directly related to the temperature and will be transient, meaning there's not a permanent change to the material, where long-term is actual degradation of the material itself due to prolonged exposure to those elevated temperatures. So take this visual here. We have glass fiber nylon 6. It's been heat aged at 150 degrees C at 1,000 hours, and you can see these nice, clean, natural bars have started to go some form of degradation. Start to discolor. You'll see some embrittlement happening with that. Fortunately, like UV, we have additives that can be used to stabilize polymers to the reactions that occur from long-term exposure to high temperatures. There's a huge variety of stabilizers out there that are used specific to the various polymers and stabilization goals that are really beyond the scope of the presentation, and frankly, my mechanical engineering background. But the point is that we have the ability to greatly reduce the long-term degradation of polymers at elevated temps with heat stabilization technologies. Again, some numbers to prove that out. Here's a glass fiber polypropylene that's been heat aged at both 140 C and 150 C for 1,000 hours. With the correct heat stabilizers, you can basically maintain those properties for the most part. In 150 C, which is really pushing it for polypropylene, can still be maintained to pass what would be considered a typical automotive requirement, or plus minus 25% retention of those properties. So you might briefly recall I mentioned a high temperature group earlier. Well, on the subject of temperature related issues, it's a good time to talk about our high temperature compounds, which are based on resins that perform well in extreme temperatures. We compound those resins with the same additives and modifiers to further enhance their properties, making them ideal for plastic parts that are used continuously in high temperature conditions, which will address both the short-term and long-term thermal issues of some of those other lower temperature polymers. Those compounds are great options when both short and long-term properties of the material must be maintained in an application. So your more high-end demanding applications, we do have a lot of good high-temperature compounds to offer that address those things. A lot of times you get some added benefits of good chemical resistance, good electrical characteristics, and some of those other things. But you're generally going to pay extra for those types of polymers. Okay, so we've reviewed a lot of problems and potential solutions. So let's take a quick look at how these might be applied in the real world and why. Let's take a look at a power drill. For this exercise, I'm not necessarily implying there's only one solution that's best in all cases, but more of an application of these technologies I've been talking about to sort of tie it all together. So let's take this power drill and broken it down into some different components. Let's say we have some chuck or maybe some internal components we can't see. The trigger or other external components similar to that, maybe this, this reverse forward button, the main drill case, and then the battery case. Let's break those down one by one and talk about them. So the main case, what we're going to need in that is good aesthetics. We want to branded, usually to whatever brand color, so pre-colored and glossy, nice surface finish. Needs to look good sitting on that shelf. We need that material to be strong, stiff, and impact resistance. It's really going to take a lot of the brunt of the abuse, and with that, it's going to get scratched and scuffed up. So we want it to be pretty resilient to that. Obviously, good chemical resistance is important because you never know what could be getting on there. And then we can potentially UV stabilize that if we think that's going to be seeing a lot of sun being left outside, whatever. So what would be a good material there would be impact modified 30% glass fiber reinforced nylon 6. That nylon 6 is going to give that good scuff resistance, glossy finish. The impact modifier helps with obviously the impact resistance, and then the glass fiber gives that strength and stiffness. So to break this down a little bit farther, we really have two options that are very common in this type of application. I talked about the impact modified glass fiber nylon 6. We also have a product under 205 HB, which is a 30% glass fiber nylon 6 without the impact modifier. But I want to talk about that because in that we have a UL 94 HB and elevated RTI rating with UL. Sometimes that UL RTI rating is going to be required for your product. That's not an easy rating to achieve. So if you're looking for something like that in this type of material for a case type material or application, that's a really good option. You do lose some of that impact resistance with that other grade, but it's still going to be quite strong and stiff, and just a good overall durable material. Next, let's look at chuck or internal components. So let's say, for example, in this component, we want it to be very strong, very stiff. We need really good wear resistance with parts, rubbing on each other potentially. These are more sensitive to geometry, so we're a little bit more concerned about dimensional shift or water absorption we might see in something like nylon 6. And maybe some of these components are getting quite hot, so we want a little bit more high temperature performance. We might look at something like a 50% glass fiber reinforced PPA. That PPA is basically a more high performance nylon. It's an easy way to think about it. It absorbs less moisture, higher heat resistance, very strong, very stiff, and we add that 50% glass fiber to further stiffen and strengthen it up. Moving on, a trigger or maybe other similar external components like that, not as critical, maybe not taking quite as much abuse. So we're more concerned about maybe the price, the performance, even though it still needs to be strong and stiff. And we just want, just a lower cost option there. Again, maybe we could look at something like that 30% XP I talked about earlier, a high performance glass fiber reinforced polypropylene. Moving on to the battery case. With that, we want a high ductility, high impact resistant material, even at low temperatures. The thing could be getting dropped. It's taken in and out of the tool. Again, we're going to want some chemical resistance there. We're going to be worried about cost. We want good dimensional stability, so it's able to fit in and out of that tool consistently. And then we want it to look good, of course. So we can look at something like an alloy being a PC ABS. They're very high impact resistance, cost effective, good finish, very common material used for battery cases and tools. So now all these attributes are great, but none of them really matter if the part is out of dimension or doesn't fit. And unfortunately, warp and shrink are some of the most common issues we see from all customers. And we often see it after a mold has already been cut. Ideally, the proper work should have been done up front with modeling, shrinkage, and design of the tool, but that doesn't always happen, or material is just prone to poor dimension. So let's take a look at some causes and solutions to that. First, we were talking earlier about those high aspect ratio fillers, good for reinforcement, things like glass fiber. That's great, but one of the downsides is they actually tend to introduce warp. Who anybody's familiar with working with glass fiber reinforced products has probably run into. So what's actually happening there is when the material is injected into a part, those fibers or whatever filler we're using that has any aspect ratio want to align in the flow direction. And what happens there is the shrink in the flow direction is reduced more than the shrink in the cross flow. So we have a differential in shrink. And when there's that differential in shrink, we get warp. See potato chipping, it's commonly referred to, and just a lot of problems that come up with that. So on the other hand, we have things like low aspect ratios, which I've mentioned, and those come in the form of minerals. Common minerals are going to be calcium carbonate, talc, mica, and I include things like glass beads and milled glass fiber and minerals, mostly just because they're all low aspect ratio, and they're all trying to accomplish the same thing, and that's to bring your shrink rate more in line with what you want. So I mentioned when you have the reinforcements, your flow versus cross flow gets affected. Or what these low aspect ratio fillers do is actually reduce that differential and shrink and give flatter parts. So with those types of low aspect ratio fillers, you get improved dimensional stability. A lot of times minerals are going to be low cost, so you actually can pull some material cost out. And a lot of times you'll actually get increase in stiffness depending on exactly which mineral you're using. So we take it, for example, some different semi-crystalline resins with 30% mineral. You can actually get around a 2x increase in your stiffness with that type of thing, along with the benefits of the dimensional stability. So if we take those two and we combine them, and let's say we need a combination of strength and stiffness that the glass fiber brings, but a relatively flat part, we can actually take a low aspect ratio like mineral filler and combine that with a glass fiber reinforcement and get sort of the best of both worlds. It's a very common approach to address warping parts or reduce or improve dimensional stability in a material. A little different approach is our low warp glass fiber reinforcement. And that's really useful for when you can't really sacrifice the properties that you get when you have to combine a mineral. So example, here's filled nylon 6s, 40% standard glass fiber. You're going to have a tensile strength around 179, but if you move to a mineral combination, you're going to lose quite a bit of that. Same with the stiffness. What we can do is introduce this low warp short glass fiber and maintain most of those properties and still improve the dimensional stability. These plaques over here are actually from my R&D days. I did a study using this low warp glass fiber technology where I could drop in back-to-back lots of 40% nylon 6, and the standard chips, these are 6x6 plaques. The standard plaques would come out all warped and potato chipped, move back to that low warp short glass fiber, and back to flat again. It was really pretty amazing. The downside is you do pay extra for that. So not necessarily go-to technology for high volume applications, but if you're really sensitive to dimensional stability and you need all the strength you can get with the glass fiber, it is a good, interesting option for that. So we take a look at all the low warp solutions we have. Generally, you're going to want to start in amorphous base polymers or an amorphous alloy, kind of like the PC/PBT I was talking about. But we can still achieve good dimensional stability with semi-crystalline materials. And we do that through the use of those fillers I was talking about, the low warp glass fiber or the low aspect ratio fillers like glass beads and minerals. And that can be applied to any part you need to, is very sensitive to flatness or dimensional stability, including router bases, the grounding surfaces like these the roll-lock bases, levels, or any part you're having maybe those warp issues with after the fact and you need a solution to. The next topic we'll look at is density modification, which really equates to making tools that are comfortable and safe to use. Both lightweighting and aiding weight, or high gravity as we call it, have their role. Making heavy tools lighter saves energy, increases comfort, And increased density can be selectively used to shift center of gravity for better balance or vibration control. We do focus a lot on lightweighting at RTP Company. I think we have as broad a range of solutions as anyone. I'll talk about those. Includes glass bubbles, our light and tough compounds, carbon fiber, and an easy way to make a part lighter is to switch it from metal to plastic. So first, glass bubbles. These are just hollow glass bubbles, so they're very lightweight. They're filled with air. If you're looking for the maximum reduction in density where properties aren't so critical, hollow glass bubbles are really your best option for that. And we can see in like a standard PC ABS, you take out 50% of the density going from a 1.14 to 0.98. But again, you do lose some of that tensile strength and you get a big drop in your impact resistance. But hollow glass bubbles do have an advantage over something like a chemical foaming agent, a CFA, which are wall thickness dependent. They don't process well. It's hard to make work right. Where once you have these bubbles in a material, you really don't have to think too much about it. They're just processed in there. You get good surface finish. Don't have to mess around with your injection molding settings and all those things that are problematic with CFA. There's, of course, things we can do to, let's say we wanted to bring some of the impact resistance back, talk about modifiers and things like that. So there's things we can do to dial in those properties if you're really looking to reduce density as much as possible. So if your part has a more demanding structural requirements, what we can do is actually take those glass bubbles and combine them with glass fiber and what we call our light and tough compounds. It's really a quick and easy way to lightweight a glass fiber material you're already using. Basically can be a drop-in replacement to whatever sort of glass fiber reinforced compound you're using. Again, not wall thickness dependent. Same shrink, don't have to mess around with any of that. And we offer that in most semi-crystalline polymers. So if we take a quick look at what those properties might look like, here's a standard 30% glass fiber nylon 6 and then a light and tough 30% glass fiber nylon 6. We can get around an 8 to 10% density reduction and basically maintain all the mechanical properties with a material that drops right in. There is a little bit of an added cost with the light and tough materials, but a lot of times that offset in specific gravity or the reduction in specific gravity offsets that cost increase. So you can about get a 1-to-1 price on a part with that reduced specific gravity and similar performance. Some interesting technology to consider. Then the last lightweighting technology I'll talk about is carbon fiber. Similar to glass fiber, it's a very good reinforcement, but it's basically just stronger and stiffer and lighter than glass fiber. It's only available in black, so that's one of the downsides. If you need a colored material, that's not an option. But if you're looking for strictly high performance, low weight reinforcement, carbon fiber is your go-to. Again, we'll take a quick look at some numbers. Here's a 30% glass fiber nylon 6 compared to a 30% glass fiber or a carbon fiber nylon 6. You get that reduction in density. You get a big boost in your tensile strength, a huge boost in modulus or your stiffness, and similar impact performance. So you right off the bat can get a reduction in your gravity, but with the added properties, a lot of times you can thin wall, take some material out and reduce the weight of that part even further. Again, carbon fiber, quite a bit more expensive than glass fiber. That's why glass fiber is a workhorse. But if you're really focused on performance and weight, it's a very good reinforcement. So let's take a look at a little case study using some of these lightweighting techniques. Here's a backpack blower. This is obviously something that's going to be, something that's going to be very sensitive to weight with the worker carrying that around all day. We worked on a couple applications, a couple parts in this application, including the backpack frame. We replaced the 30% glass fiber polypropylene with a 20% carbon fiber polypropylene. There's over 10% weight savings, and the part was nearly 2 times as stiff. So weight savings and improved stiffness and performance. And then with this orange colored outer case, we replaced the regular 20% glass fiber nylon 6 with our light and tough compound. We achieved that 8 to 9% density reduction. Was still able to get that orange brand color and nice surface finish, not possible with something like CFA, and dropped right in on the same tool. And as I mentioned, we can actually use higher density to accomplish some things. That would include vibration and sound dampening, or sound damping, center of gravity adjustment, and sometimes just giving an expensive feel. Probably not relevant with tools, but maybe there are applications where a tool feels cheap. You actually want to add some weight. High gravity compounds can do that. And this chart really breaks down the range of densities we can achieve. 1 being the density of water, 11 being close to lead. Our low gravity compounds can get below 1, and we can go anywhere up to basically the density of lead with these high gravity compounds, using various filler technologies. So that wraps up the more technical side of the presentation, but there's a lot more than just the material side of issues common in the tools market. And those have to do with things like economics, efficiency, innovation, and seamless production. So I'd like to jump into how our RTP company can support you on that side as well. So a very common issue we've seen with tool manufacturers is trying to wrangle all the different locations and materials into a streamlined portfolio of standard products. Often what that looks like is one location is using their own group of materials, another location using a group of similar but different materials, maybe different supplier, different grades. That could be true with the design team, the engineers, the molders, whatever. And what that results in with all the different grades and different locations is a design and logistics nightmare. We're a global company. We have global account teams to help tie those things all together. And what that really looks like is we can reduce suppliers and material grades, and we can do that in local production, as I mentioned. Kind of a new hot topic of recent is tariffs. So when we have local manufacturing, sometimes we can get around some of those issues. When you reduce the amount of grades you're using, you can leverage that through improved pricing. Obviously, easier logistics, easier product support. It's easier for the technical teams to know what to design with when they have a consistent group of materials to choose from, instead of everyone trying to reinvent the wheel all the time. And we see that just manifest in a lot less mistakes because there's better communication, and we have the team to really help tie those things together. Saves a lot of headaches for some of the larger companies we work with. Just to drive that home, here's a slide literally showing our global footprint of sales and support. We have sales on the ground in any area you manufacture. In the rare case we don't have a salesperson in the location, we do work through distribution. But I mean, realistically, anywhere pretty much anyone's making things, we have a footprint there. Along with sales support, we have engineering support in each region as well. Having local engineers available to visit customers results in a lot quicker problem resolution. Additionally, local engineers work with and maintain a good understanding of the local raw materials, and that results in a safety of supply and competitive pricing by just using things that are locally available and that's cost effective. For example, during the COVID supply chains, not having to ship things all over the world really saves a lot of that risk. Along with that, we also have a field of tech service engineers. I consider our tech service engineers really the unsung heroes of the company. These are the guys that are going to go in at tool trials, mold trials, ramp up, production issues. They're going to go in there. They're going to be our eyes and ears on the ground. They're going to help diagnose improper settings with injection molding, mold and tool issues, corroborate issues. For example, if there's a lot issue at a customer, they can corroborate maybe there is an issue with that lot, or they can say, this is not a material issue. And these guys just are invaluable, and we love to have these guys supporting our customers throughout the whole process and get them up into seamless production settings. Part design is another overlooked area where costly mistakes can happen. It's much cheaper and faster to get things done the right first time around than to try to fix the problem down the road. So we can go in, help diagnose any issues with parts, but we can also find parts that might be a good option to do a metal to plastic conversion, optimize the plastic design, or let's say we've identified parts or you've identified parts. We do have a CAE support team that can start to do things like mold flow, look at your part design and say, if we get there, we're going to have issues. Just all the things up front that are entirely too often overlooked and cause problems. Getting us involved early will help avoid those issues, and we love to partner up to do things like that. I know there's been a lot of information, and I'm just scratching the surface with one of our many product groups. So there's many more technical resources at RTP Company to take advantage of. We love to share those resources free of charge for our customers. We do regional technical workshops. We can come to your location, or we can host you in any of our locations. One very well-received way of doing that is our lunch and learns, where we'll cover a couple topics over a long free lunch for employees, which is a good way to increase attendance. And those, I do a lot of those myself. Really a great way to inform people new to the industry, or even people that have been in it for a while, about what's out there with thermoplastics, things that can be done. Very useful. And then a lot of times that'll end with a great discussion where you start spitballing, oh, hey, I had this problem. What can we do to solve that? And a lot of things get done in those types of meetings. And I do have my marketing folks on the webinar here, so I would be remiss in not plugging our rtpcompany.com website as a great educational resource. There's tons of good information on that. It's free to the public. Even if you never use us, go ahead and poke around on there. You'll find something useful, I'm sure. And then finally, I'm going to close on a topic that seems unavoidable in any discussion these days, and that's sustainability. It's becoming a key driver in some market segments, and it's just more and more prevalent. What I'll say is we see it, and we have solutions for those needs, including recycled solutions, post-consumer, post-industrial recycled, plant-based or bio-based solutions, including polyolefins, polyamides, polyesters. And if you're looking just for ways to reduce carbon footprint, we have a range of options for that as well. So if sustainability is becoming a hot topic or something that's something that you're pursuing, we definitely have some solutions for that. So to close out, we really do best as a company when you're a partner and solutions provider. Specific to tools, we have plenty of technologies and solutions. I'm just talking about structural today, but obviously with all those other product groups, conductive, flame retardant, I mean, the opportunities are endless for our solutions to help you out with that, I mean, we have, I think, as diversified product portfolio as anybody out there. We have the technical expertise to support that, the global production and support, and just want to drive home one last time that along with the technical expertise, we're a big player in high volume, very competitive markets, and we love to play there now. So don't count us out if you think we're the specialty compounder. We can compete with anybody. So with that, I want to thank you for your time. I hope it's been informational. I'll open up with some questions if there's any out there.
Thank you. Let's take some questions from the chat window.
First question I see is how are the XP compounds priced compared to short glass or long glass compounds for the polypropylene? The XP, just like their properties, are going to be priced sort of in between a standard short glass fiber polypropylene and a long glass fiber polypropylene. Thank you for that. Next question, do you have to use multiple compounds for different tool parts? If so, can the color be matched? You don't necessarily have to use different compounds for different tool parts, but the goal for any product is to have the most cost optimized solution for those parts. So for example, that power drill, we don't necessarily want to use PPA for the trigger if that's overkill. So we can use something like a glass fiber polypropylene. And if you do have those branded colors, we can color match very effectively with the various materials. Next question, at high glass loadings, what is the effect of boiling PA6 or PA66? Is it necessary to achieve dimensional stability? So nylons in general, especially the lower chain nylons like nylon 6 and 6.6 are hygroscopic, meaning they do absorb moisture, and they can absorb moisture from both the air or being exposed to water directly. The higher the amount of glass loadings, the less polymer there's going to be to absorb moisture. So generally the effects of the moisture absorptions decreases as the amount of filler, whether that's mineral fillers or glass fiber, goes down. Is it necessary to boil anything to achieve dimensional stability? No. Generally, that's going to level off at a sort of equilibrium state over time on its own. Sometimes what we see with customers is the nylon products can be sort of brittle right out of, it's called dry as molded, right out of the mold. And they'll do things to speed up that process of moisture absorption. And that can be through heated water, dunking in water over the weekend, just letting them sit out for a week and things like that. Yeah, I hope that answers your question. There's not any other questions. I will wrap it up. Again, I appreciate everybody's time. This will be available to anybody on the webinar, and will be available after the fact as well. We'll be sending out a PDF. So with that, I will thank you and wish you a good weekend.